common ion effect was a way of reducing the solubility of an ionic compound. All of these equations are just real similar. They're the dissociation of an ionic compound, where you'd start with your original solid and it dissociates or separates into its charged ions. So yeah, if I add one of those ions, Le Chatelier's principle would say then you shift away from what was added. So if I add magnesium ions, for example, I would reduce the solubility of magnesium hydroxide. However, there are also ways of increasing the solubility of an ionic compound. One option is to dissolve your compound in an acidic solution. Hydroxides are often more soluble in an acidic solution. And so we had this example from, actually with the Le Chatelier's lab. Magnesium hydroxide is in milk of magnesia. It's kind of a chalky solid. It's not real soluble, it's only slightly soluble. But we added acid, and as we added acid, all of a sudden the solution gradually cleared. Well, the hydrogen ions from the acid react with the hydroxide that is produced. There's a small amount of hydroxide produced. And together they form water. Now, water is a liquid. It's not something that is fully ionized. Way back in the Le Chatelier days, we did a lab where we formed like a precipitate. We precipitated some chlorine by adding silver. Silver chloride was an insoluble product. So it's a way of removing an ion, form something that's not fully ionized. But besides a precipitate, forming liquid water is another great option. So often hydroxide compounds that may only be slightly soluble in water do become more soluble in a slightly acidic solution. Where the hydrogen reacts with hydroxide, you'll form water, and that does remove the hydroxide. And if I remove a particle, I want to shift to replace it. So yeah, I'd be shifting more forward, which means then that more magnesium hydroxide will ionize. Another option is to add an acidic solution to a compound that contains the conjugate base of a weak acid. Look at us with all this equilibrium lingo. So for example, they're giving me a Ka of hydrofluoric acid, and I notice that it's small. So the Ka is small, I know that this must be a weak acid. Well, the conjugate base of hydrofluoric would be this fluorine ion. So kind of a similar situation happens where if I dissolve silver fluoride in a solution that's acidic, there would be hydrogen ions present. Well, obviously the hydrogen can't react with the silver or the magnesium. It's two positives, but a positive could react with a negative. And so the hydrogen from the acidic solution could react with the fluorine, and together they would form HF, hydrofluoric acid, which even though I would label it as aqueous, it's a weak acid. And I know that weak acids do not extensively ionize. I mean, this thing might ionize by less than 5%. So it is a way of removing that fluoride ion from the solution. We could form a precipitate, a solid, that would remove an ion. We could form liquid water, that would remove the hydroxide. Or we could form a weak acid. And again, this works if I form a weak acid because it is not extensively ionized. So 99% of the hydrogen will react with the fluorine and form something that is not dissociated. So it's as close to like a liquid as we can get. Only a very small portion of those HF molecules might redissociate to form hydrogen and fluorine ions. But it is a way then of increasing the solubility of the original compound.